So now we've seen that we can calculate the energies which are allowed for an electron in an infinitely deep well using the equation the energy of the nth level is equal to h squared over 8ml squared times n squared, where n is an integer representing the level. So we can represent these energy levels on a diagram such as this one. So in this diagram, the lowest state, that's the state with n equals 1, is called the ground state. So that's the lowest allowed energy level for an electron in the given potential well. The next state up with n equals 2 is called the first excited state. Then we've got the second excited state for which n equals 3, and so on. So the really important point is that these energy levels are quantized. An electron in the well can't just have any random energy, it has to have one described by the equation that we've just written down. Now, to move between levels, if we have an excited electron which wants to drop down to a lower energy state, then it needs to release some energy. So it can release a photon, and we can work out exactly how much energy that photon has to have, because it has to correspond exactly to the difference in energy between the two levels. Likewise, if an electron wants to move up levels, then it needs to absorb a photon with exactly the right energy to get it up to the excited level that it's going to. So in a minute, we will rearrange our energy equation to work out the wavelength of the photons that can be emitted as an excited electron drops down to lower states. So let's calculate those wavelengths now. So what we want to do is find lambda as an electron transitions from an initial state with energy E initial and a quantum number n initial, so this n is just an integer, to a state with energy EF and quantum number NF. So we'll have it going down levels, so we'll have NF smaller than N initial, but we could use exactly the same method to get the wavelength of a photon it would need to absorb if it was going to jump up a level. Okay, so the energy of the photon is equal to the difference in energy between the two states. So it's losing this energy, so it's EI, the higher energy, minus EF, the final lower energy. And we know that the energy of the nth level is equal to h squared over 8ml squared n squared. So we can pull h squared over 8ml squared out as a common factor, and then we've got n initial squared minus n final squared. So that's the energy for our photon, but we're trying to get lambda. So remember, E is equal to hf, which is equal to hc over lambda. So now we've got our energy in terms of lambda, so what we'll want to do is equate these two things. So we have hc over lambda, which is equal to h squared over 8ml squared, times the initial n initial squared minus n final squared. Now we're trying to find lambda, so let's cancel off these h's, and then we end up with an expression. 1 on lambda is equal to h over 8mcl squared, n initial squared minus n final squared. So we can use this expression to calculate the wavelength of the released photon. Now what's interesting is this is somewhat similar to our Rydberg equation. It's a little bit different in that we do have a slightly different n dependence. The Rydberg equation is given by 1 over lambda is equal to the Rydberg constant times 1 over nf squared minus over 1 minus n initial squared. And as we'll see later in this course, when we're deriving the Rydberg equation here, we go through almost exactly the same process as we went through for our infinitely deep potential well.